Yeah, there you go.
Okay, so it's a pleasure to have Professor Luiz Santos here today to talk to us. Professor Santos did his bachelor's at the Universidade Federal do Espírito Santo in Vitória, Brazil, in 2004. He got his master's at the University of Kentucky in Lexington, United States, 2007. And his PhD in 2012 at Harvard University. Then he had 2 appointments as a postdoc researcher, one from 2012 to 2015 at the Perimeter Institute for Theoretical Physics in Canada, and 2015 to 2018 at Urbana-Champaign in Illinois, United States. And since 2018, he's an assistant professor at the Department of Physics at Emory University in Atlanta, United States. So, Professor Santos, it's a pleasure to have you here today. The title of his talk is Superconductivity in Hofstadter Systems from Repulsive Interactions. Thank you very much for accepting our invitation. The microphone is yours.
Okay, thank you, Jorge. Thank you, Edson, for the kind invitation to be here. You know, it's a real pleasure to talk to you for the first time and to interact with you colleagues in Uberlândia. I've never been to Uberlândia, but I have many friends in Minas, so hopefully someday I'll be able to visit and, you know, we can discuss some physics in person. I see a couple of people here. Is Rodrigo Pereira the one who I suspect it is? I don't know, let's see. But hey, Rodrigo, good to see you. Good to chat with you, I guess. Long time no see you. So it's you know, I'd like to share with you some of our recent results on a problem that is traditionally very much associated with quantum Hall physics, but on which we found some very surprising results related to superconductivity, and that's the problem of electrons in a two-dimensional lattice under magnetic field, a problem that is an iconic system that was studied by Douglas Hofstadter back in the 70s, and has played a very huge influence in the development of modern condensed matter physics, in particular topological phase of matter. So before I do that, let me acknowledge the young fellows in this collaboration. I'm already an old dude, so the heavy piano was carried out mainly by my postdoc, Daniel Schaefer, and also by my former graduate student, Jian Wang, who graduated this past summer and is back in China. So this work is, I'm going to be talking about two works that are on the archive. One is published in PRB as well, and the second one is under review. And you can find the references here. So let me jump ahead and tell you what the problem is. So we are interested in understanding the behavior of electrons in a two-dimensional lattice under a perpendicular magnetic field. So this problem, as I was alluding before, is an iconic system that Douglas Hofstadter solved many years ago using computer simulations, and he finds that the spectrum of the system has an extremely rich fractal nature. So energy levels as a function of the magnetic flux phi per unit cell divided by the fundamental flux quantum h over e shows this remarkable fractal behavior. And what this system here described then is a bunch of fractal electronic bands that are extremely sensitive to variations of the magnetic field. The flux per unit cell is field times the area of the unit cell, b times a square, and phi naught is h over e. So, of course, this is a remarkable system, but for a long time, this system had been subject to only theoretical analysis, and the reason is the following: is that in typical magnetic fields you can access in laboratories of the order of a few Tesla, and in typical two-dimensional lattices or heterostructures you get, the A is of the order of angstrom, so few Tesla times angstrom square, gives you a flux which is typically much, much smaller than the fundamental flux quantum H over E. So usually when you take a system like graphene, or you take gallium arsenide or some typical 2D electron gas, phi over phi naught turns out to be a number very, very small, of the order 10 to the minus 4, 10 to the minus 5. So one is usually probing this very lower corner of the spectrum, which is dominated by a series of Landau levels. So that's a problem in which you kind of throw away the information about the lattice. There's an emergent Galilean invariance in the problem, and you deal with electrons with a dispersion p squared over 2m and some effective mass m describing them. Okay. Another way to see this is that there are two scales in the problem. One is the magnetic length, LB, which is 26 nanometers divided by the square root of magnetic field measuring Tesla. So for fields accessible in laboratories, this is tens of nanometers typically. Whereas you want to contrast that with A, the lattice spacing. So in regular, materials, this is of the order angstrom. So, it's a huge difference in energy scales. Okay. Nevertheless, Hofstadter bands had been caused a lot of excitement because they provided a natural framework to understand topological phenomena, in particular the quantization of the integer quantum Hall effect. Going back to the works of Paulus and collaborators, it was realized that for each of the, when you have an insulating state, when you're filling an integer number of these bands in the Hofstadter spectrum, and there's a gap separating, and your thermal level lies in a gap, then the integral of the Berry curvature over all the occupied bands turns out to be an integer number. This integer number is called the Chern band, the Chern number, and that shows up in a physical property as the quantization of the transverse Hall conductance. Okay, so, but in recent times, in recent years, there's been extremely remarkable developments in material science that were made possible by the fabrication of so-called moiré quantum materials. So these are two-dimensional materials that are layers of two-dimensional materials that are twisted with respect to each other over small angles. And what it creates for you, it creates an emergent lattice that has an effective periodicity which is much, much larger than the underlying lattice constant of each of the layers. And therefore, it creates a super lattice where the effective length scale is of the order of nanometers. Okay, so that gives you the possibility of having the magnetic length being comparable to the lattice constant in these systems. So this system is extremely rich for several reasons. One is because there's it's a system in which you have an emergence of flat bands that on which superconductivity had been observed, and that caused, of course, a lot of excitement in the past few years. But also, when you apply an external magnetic field, as I was saying, now your unit cell is so large that B times A can be compatible to phi naught. And that puts you precisely in this, puts you precisely over here, where you can start to deviate away from this Landau level regime, and you can start to probe this very rich structure of fractal bands. Okay. So this is one of the measurements that was done, revealing capturing the properties of these fractal bands by transport measurements. Okay. Okay, so maybe repeating myself, but it's never. It's also important to emphasize that over here we have Landau levels. These are very degenerate states, and they're equally spaced. And what characterizes them is that the separation between the states is very, very small compared to the entire bandwidth of the system. Whereas if you go to the fully into the Hofstadter regime, where the flux is compatible to phi naught, for example, at 1/3 flux quantum, then your spectrum looks very different. Now we have 3 bands. They are separated by some gap. They have a lot of curvature. They have a lot of character. They have a lot of lattice information, and they don't look anything like Landau levels. So it's a very different regime. Phi over phi naught is order 1 now. It's some some fraction of phi naught. And what's very interesting here is that the scales of the problem now are compatible to the full bandwidth of the system. Okay, so you're in a very different regime, and my motivation, my sort of the overall picture is to try to understand what kind of new phenomena you can get when lattice effects become important. And in particular, I'm going to be exploring the possibility of superconductivity in these systems. So let me give you a quick reminder of some of the basic properties of the systems, and one is the notion of magnetic translations. So in the absence of a magnetic field, if I have a lattice with some translation symmetry T1 and T2 over perpendicular or over linearly independent directions, then T1 and T2 commute with each other. So if I perform a translation by T on the horizontal bond, it's followed by translation by T2 on the vertical bond, that's equivalent to doing vertical bond first and horizontal bond first in the absence of a field. In the presence of a magnetic field, things change. Things change because as you go around the unit cell, if this flux is not an integer number of phi naught, then your electron is going to experience an Aharonov-Bohm effect. It's going to experience a flux, which is e to the I phi over phi naught, and that tells you that the action of the translations along x and y directions do not commute anymore. And the statement is that you want to change your regular translations, promote them to magnetic translation operators. They still commute with the Hamiltonian, however, they don't commute with themselves. Okay, and of course, you know, this is something that's known long ago, going back to the works of Zach, Brown, and many others. Okay, so in my notation in this talk, I'm going to always be dealing with rational fluxes. I'll make some comment about the rational fluxes very in passing, but here I'm assuming that phi over phi naught is some rational number that I can write in the form P over Q. Okay, and I'm going to stick to that. Okay, what's interesting about this? What's interesting about this is that because of this algebra, you see the irreducible representations of the single particle states, in other words, the bands of the system, they become Q-dimensional, where Q is the denominator of the flux. So this just means that your zero field bands are now split into Q other bands, and more remarkably is that each of these bands is itself Q-fold degenerate. So this magnetic translation symmetry over here that acts in real space, when you work it out in momentum space, implies this particular relation on the energy bands. So in other words, if I take my K point somewhere in the Brillouin zone and I shift by a vector which is proportional to the flux, then my band repeats itself. And it does this Q times. So each of the bands is split Q times, and each of these bands is also Q-fold degenerate. Okay, so this is an example of flux 1/3. Now, what good does it do to you? Well, this creates a very interesting kind of situation that you normally don't find in typical band structures, that now your magnetic, because of this magnetic translation symmetry, your Fermi surface is very organized into patches. Right? So imagine I make a cut over here. This is my chemical potential that I pass somewhere over here. What I'm going to have is a series of Fermi patches that are degenerate with respect to each other. And if I take my K vector over here and shift by a vector that I call Q, which is a vector proportional to the flux, then I find myself in another patch, and I find myself in another patch, and I do this Q times. Okay. So, you know, this creates a very interesting situation where, you know, because your Fermi surface has many patches, if you look at the possibility of fermionic instabilities, such as superconductivity or spin density wave or charge density wave, that creates a rich structure for you to explore. And you know, this scenario, you know, leads to the possibility of interesting competing intertwined orders that has been the study of has been the subject of my study recently. Very good. So this is non-interacting physics. Now I want to think about interactions. I want to say, suppose I have a very general interaction, and for now I'm just going to talk in generalities In the second part of my talk, I'll give you a very specific interaction, and we're going to see how this works. But now let's just say I have a local interaction, okay, that I start on the lattice, and I project on this band, and I project this interaction on all these patches on this band. So what I have is I have a bunch of 4 Fermi operators, 2 creation operators, d dagger, 2 annihilation operators, dd. L and N are patch indices, so they are running between 0 and q minus 1, and p is the momentum relative to the patch. Okay, and so you have a process that you would represent somewhat like this. Now, magnetic translation symmetry kicks in already over here because since these d operators transform under each other under a magnetic translation symmetry, there has to be a condition relating the coupling constants as the electrons scatter between the patches, and that enforces symmetry conditions like these on the couplings. Okay, so let me think about the problem of electronic pairing in these bands. And I'll attack this problem by considering a generic mean field pairing Hamiltonian. So this mean field pairing Hamiltonian has a normal component, which is a sum of electrons on each of these q patches, and E epsilon of k is the dispersion near the patch. And then I turn on a very general pairing Hamiltonian that involves pairing of electrons between all the possible patches that I can have on my Fermi surface. Now, from the outset, something very remarkable happens over here. Is because unlike the situation in a single Fermi surface, where you're typically around the gamma point and you're pairing electrons between k and minus k, here the patches are displaced in momentum space. And so if I take an electron from one patch over here and a pair with another electron from another patch, the Cooper pair that involves that pairing will carry a finite center of mass momentum. Okay, and that shows up in the way you write this pairing operator over here. Now, this symmetry also shows up in a very interesting way. So if you write the linearized gap equation for this, because of the constraints imposed on the coupling constants G that I had in my previous slide, that means that I have a very set of degenerate solutions of the gap equations because of the multidimensional reducible representation of this group. And the solutions of this gap equation can be classified by understanding the irreducible representations of the magnetic translations, but not of the magnetic translations acting on the single particle electrons. That is a very old story worked out by Zach, Brown, and others. But now I want to think about how does the pairing order parameter transforms under magnetic translation symmetry. So I'm not taking one electron and transforming, I'm taking a pair of electrons and acting with the transformation. And this turns out hadn't been fully explored before, and our paper has provided what I think is a very comprehensive classification of symmetry groups of this problem. So the gap equation couples this order parameter with fixed momentum L. So L is the momentum. L is the total momentum of the pair, let's say in the y direction, along the direction ky, and because there's a conservation of momentum, you can assign a q by q matrix in which you write all the possible pairings of electrons that have a fixed total momentum big L, and they will form a component of this irreducible representation. And then you can say, now let me act with the translation operator on this multi-component order parameter. How does it transform? Well, each electron is shifted by 1, but since you have a pair of electrons, the whole thing shifts by 2. And so an order parameter that's labeled by capital L under the action of T1, which sends my ky by 1 unit, is shifted by L minus 2. And Ty just provides a phase factor to the order parameter. So what kind of physics comes out of this mathematics? A very interesting type of physics. So if you work out this algebra over here, you can show something very general about the problem. You can show that this order parameter that involves pairing of electrons cannot exist if you try to simultaneously preserve T1 and T2 symmetries. So there is no non-zero order parameter that will be fully symmetric under the full magnetic translation group, which means that if somehow there is an instability on these Hofstadter bands that causes pairing of electrons, it must be that this condensate breaks at least partially the magnetic translation group. You might fully break it, but some of the generators have to be broken. Okay, and that also implies that there are degenerate condensates that carry different momentum, and this different momenta are related by actions of the magnetic translation group. So there's a possibility of a very degenerate set of low line states. And the reason for this is very simple, is because of the Aharonov-Bohm effect. Essentially, you can see over here that the action of the magnetic translation generators involves a phase factor, which is a U1 phase. So if you go into a condensate that breaks U1 symmetry, like in a superconductor, that will imply that some of the generators of the MTG will have to be broken as well. So that's the physics that comes out of this mathematics. So you also want to understand how many of these irreducible representations. Suppose you're trying to write down like a Landau-Ginzburg theory that describes the phenomenology of this superconductor. You want to know how many components you want to have. Is it 1? Is it 2? Is it 3? Is it 7? How many? And that answer is answered by counting the dimension of the irreducible representation. And here there is there are two classes. So if this denominator here is odd, Q is odd, then what happens is that you're always taking a member of the reducible representation with total momentum L and shifting by an even number n, which is 2. And that means if you start with Q equals odd, you have to act with this generator Q times before you get back to the initial state you had. So for example, if I have an order parameter for which I am pairing electrons on 3 patches of the Fermi surface with total 0 momentum, I would take an electron from this patch, which is near the gamma point, and pair this point with that point. I could also pair an electron from here with that Fermi surface, that's also 0 momentum, and I can also write the reverse process. But then if I act with the magnetic translation, I'm going to be shuffling these electrons around on the patches, and that means that this order parameter here will be mapped into that order parameter, and then this order parameter will be mapped into that order parameter, and finally I come back to this one. So there are 3 components, which means the irreducible representation is 3. And this pattern resists for odd Q. Now, if I have even Q, the situation changes because, well, I may have a commensurability with 2 over here. So I start from 0, go to Q minus 2, and then I go to Q minus 4. So if I start in the odd Q sector, I remain in the odd Q sector. But if I start in the even Q sector, I remain in the even Q sector. So this 2 representation is split into 2 classes. And you might suspect that there are perhaps 2 irreducible representations, 2 classes thereof. But in fact, there are 4 irreducible representations with dimension Q minus 2. So this is a little technical, but let me just get it out of the way and just give you a flavor for how this works. So suppose you have Q equals 2, which is a pi flux case. So there are 2 patches on the Fermi surface. And I can write an order parameter that pairs this electron with this patch, and another one that pairs this electron with that patch. I can also so this will be a 0 momentum order parameter, but I can also pair this electron with that patch, and vice versa. This will be a momentum pi order parameter, and under magnetic translation, this maps into that. So I would have a 2x2 matrix. But there's a choice of signs here, plus or minus, depending on how they act with respect to TX symmetry, and that explains why you would have 4 irreducible representations with dimension Q minus 2. This is a little technical, but I just need to spell out the result. Okay, so what you should understand from all this story is the following, is that if I'm trying to pair electrons on this multi-component patch Fermi surface, I end up with a multidimensional order parameter. okay, which scales with Q, Q being the denominator of the flux. And so I have a Q component complex order parameter, then I know exactly how it transforms under all the symmetries. So if it's charge 2, it transforms under exactly as you would expect under charge 2 of transformation under U1, and also under T1 and T2. So once I have a classification of this multi-component order parameter, I can write down the most general Landau-Ginzburg theory that preserves all the symmetries. Okay, and this is a multi-component field theory that can have a very rich landscape of minima, and each of these minima can correspond to different ground states in which you go. Okay, so that's kind of the message over here. There is one class of these superconductors which we call ZQ symmetric solutions, those that preserve under the action of Tx. And they are characterized by solutions in which all the components of the order parameter have the same magnitude. If Q is sufficiently small, you can always find global minima for this that corresponds to these ZQ symmetric solutions. When Q becomes very large, then you find that this global minima may or may not be, the symmetry may or may not be broken, and this, it's a problem that requires some insights from microscopic physics to understand what are the possible phases and what are the values that these parameters ought to take if you're considering a particular lattice model. But here we just do a very simple numerical analysis. We take this Landau-Ginzburg theory, we make some phenomenological parameters, and we vary them, and we look for the ground state. And you find a remarkable rich structure of ground states in which this superconductor, this order parameter, becomes non-zero, and sometimes it fully breaks the symmetry, sometimes it doesn't fully break the symmetry, and there are first-order transitions, as you can see here, characterized by these jumps. We also find continuous second-order transitions in which the gap closes and opens very smoothly. And so, the message is it's a very rich problem that one should take into consideration. Now, we classify this problem in very great generality, but I should mention that there had been a number of earlier numerical works that had found through mean field calculations realizations of these phases. These are typically situations in which we have Hofstadter model with Hubbard interactions, or you have an integer quantum Hall state proximatized by superconductors. So what happens in these scenarios is that the electrons will pair, but they will form a vortex lattice. Okay, and you can see a very rich structure of that's characterized by texture of the order parameter. Okay, so let me make a comment about rational versus irrational flux. I don't know how fast I'm going. You slow me down if you want, but it's always hard to gauge oneself when you're talking online. But let me just make a very general comment about irrational flux, which I think is important. So we are studying a particular rational realization of these Hofstadter superconductors, let's say at flux 1/3, where, for example, I could be looking at this particular band. And you might ask, what happens if the flux changes a little bit? What if it's not 1/3, but if it's 1/3 plus or minus some fraction, that's very, very small. And what the spectrum tells you is that these bands here, they start to fan out, they start to split again, and because of the self-similarity of the spectrum, the way that this band split over here is very similar to the way they split over there. So there's a repetition on the pattern of gaps in the Hofstadter spectrum. But in general, you can always make the argument that if you are near a rational flux for which the microscopics of the problem, for which there's a pairing condensate of some scale delta, then if you vary the flux around here, what you're going to do is you're going to break that band into small bands which look like pseudo lambda levels. They have a very small separation of energy scales of the order of an energy scale that are called h bar times omega c effective. So this is like an effective lambda level, but to the extent that this delta is much larger than h bar omega c, there should be stability to the to that condensate, just like type 2 superconductor is stable to the application of a small magnetic field, right? So the order parameter starts to decrease as a function of field, but it doesn't die immediately. And there have been some earlier analysis of pairing in lambda levels, showing that when the magnetic field becomes sufficiently large, that with phenomenologically attractive interaction, it is possible to for electrons to pair up again in large magnetic fields, and this is often called re-entrant superconductivity. So this is our context is very different from the usual story of re-entrant superconductivity, because we're not dealing with lambda levels, we're dealing with fractal electronic bands, but there are definitely similarities in the way you can understand these systems. I want to talk a little bit about microscopics in a few minutes, but maybe I'm going too fast. Are there any questions?
Not yet.
No questions. Okay. Yeah, I feel like I'm really running here, so stop me if you want. Okay, so right. So in this first paper that I alluded to, where we classify Hofstadter superconductors, we've shown that there are sort of like two kinds of phenomena that can occur when you have spin polarized bands that form one of the ZQ symmetric superconductors. One is that they can give rise to topological superconductors. In other words, superconductors that are characterized by bulk non-zero Chern number, and therefore they carry chiral propagating Majorana modes on the boundary. There's a very interesting result you can show, is that if you are in one of these, if you're protected by that ZQ symmetry, that the Chern number that you get in the case of spin polarized band is fixed. The parity of the Chern number is fixed by the parity of Q. So in other words, if you have Q equals odd, there will be an odd Chern number. If you have Q equals even, you're going to have an even Chern number. And that's a very, very nice result that's highly constrained by the way that these electrons are paired. But of course, that result stands to the limit that you're dealing with spin polarized electrons. There's also something very interesting about the systems. If you couple ZQ symmetry with inversion symmetry, then you have the possibility of Bogoliubov Fermi surfaces. In other words, you have the possibility that electrons are paired, but on a ring in momentum space, your order parameter vanishes, and that means you really have a Fermi surface, but a Fermi surface of Bogoliubov quasi-particles. There's a great deal of work that proposed these phases, and it was very surprising to us that we ended up finding them in a system that is traditionally associated with quantum Hall phenomena. Okay, but let me raise a question which is much harder. So right now, what have I done? I proposed the following problem. I said, let's look at these bands. Okay, these bands have a very interesting single particle physics property that general bands don't have, is that you can control the repetition of the energy, the energy spectrum repeats itself, and the bands are self-similar. So if I change the flux per unit cell, I'm also changing the number of patches in the magnetic Brillouin zone. This is a remarkable property of these bands. And I showed you that if I assume that superconductivity arises, that it's a multi-component order parameter, the dimension of this order parameter scales with Q. and there are all kinds of interesting exotic superconductivity that can occur. But I haven't told you how to realize that, right? I just told you that let me write down a mean field Hamiltonian and just hope that nature or some microscopic physics might realize it. Now I want to raise that question, which is much harder question. I want to look for a mechanism, a microscopic mechanism on the lattice scale, some kind of local interaction that I can write down the lattice scale, and I want to argue that there is such an interaction that realizes this rich phenomenon. So where am I going to look for an inspiration to attack this problem? It's an extremely hard problem. It's a very hard problem because I don't want to think about phonons. I want to think about electronic interactions only. I want the system, I want to find a situation in which I have a Fermi surface under which, driven entirely by electronic interactions, there is an instability of that Fermi surface towards one of these Hofstadter superconductors. That's what I'm trying to find over here. Well, I'm going to look for inspiration in an iconic system, which is the square lattice nearest neighbor model, which is which is a model that's very relevant to understand the physics of cuprate superconductors. So I'm going to go to the square lattice in 2 dimensions. And what do I know about the square lattice in 2 dimensions? Well, I know that if I have a single band, some cosine kx plus some cosine ky band that we all know how to solve in solid state physics, and if I go near the gamma point, I have a parabolic band. Okay, I have some nice parabolic band with an effective mass. If I go near the corners of the Brillouin zone, I have an inverted band. So I have minima over here, maxima over here. But somewhere in between, I have to cross. I have to cross over the region in which I have electron-like excitations to the region where I have hole-like excitations. And that transition is picked up by the presence of von Hoff singularities. On the square lattice, I have at chemical potential mu equals 0, which means that precisely at a half filling, I have this very nested Fermi surface which is connected on the 2 sides by a wave vector pi on the square lattice that takes me from any point over here into any point over there, and from any point over here to any point over there. And this Fermi surface, this parallel Fermi surface, this perpendicular Fermi surface, they meet at the points pi 0 and 0 pi on the boundaries of the Brillouin zone. And these points are precisely the von Hoff singularities that you have. So what happens if I look at the density of states as a function of the energy, I start over here near the gamma point, I end over here near the pi point, but somewhere in between, in this case precisely at the center at E equals 0, I see that my density of states has a logarithmic divergence. That is the manifestation of a von Hoff singularity. Now, this is an extremely interesting point to look at, because properties of electronic states all depend on density of states. And if I have density of states that are diverging somewhere, then I can hope for interesting instabilities of that Fermi gas into something more interesting. What can happen? Well, I could have an instability towards a charge density wave. I could have an instability towards a spin density wave, or let's hope I can have an instability towards a superconductor. Okay, and because of the perfect nesting of this Fermi surface, the susceptibility towards pairing of electrons, in other words, the particle-particle susceptibility, has a logarithmic divergence, as well as the susceptibility towards spin density wave, which is a particle-hole susceptibility. Okay, so so there are these 2 logarithmic stabilities, and you can hope that particle-particle processes and particle-hole processes will start talking to each other, and the physics at low energies might give you something interesting. So the way you can understand this problem is by what's called a patch model. So you expand your fermion operators near these patch points, near the two von Hoff singularities, pi 0 and 0 pi, and you write all the possible phenomenological interactions that involve two particle scattering processes. There are 5 of these coupling constants, G1, G1 prime, G2, G3 prime, and G4, and they're related by intra processes or interprocess or exchange or pair hopping. Okay, very good. So what has been shown a long time ago by these authors over here is that if you do the renormalization group analysis of this problem, in other words, if you write down an effective theory that involves these two patches, and you start integrating out the high energy modes towards the von Hoff singularity, that you can explain the onset of D-wave superconductivity induced by the proximity to large spin fluctuations, to a spin density wave instability. And that happens in the nearest neighbor model at one loop RG, provided you deviate a little bit away from this perfect nesting condition. Okay, that's a result that's known a while ago. So this provides a mechanism for pairing induced purely by repulsive interactions. I think there's a question.
Luiz, yeah, there is a question. Rafael, go ahead.
Yeah, thank you. Just a little bit. I don't know if I missed something, but why do you consider only those two patches? Or just a drawing?
Right. Because the idea is that there's a logarithmic instability associated with divergent density of states over here. So technically, there are two logarithms involved here. So when you calculate this susceptibility, there is a density of states that shows up over here, and there's a log that comes from the Feynman diagram itself. But because the density of states diverges near those points, those provide the dominant processes. Yeah. So it's the fact that you have a large concentration of density of states near those patches that allows me to first approximation. Of course, and one can do a much more involved calculation that involves scattering throughout the entire Fermi surface, but it's pretty reasonable to argue that to first approximation, those are going to be the terms that really dominate the physics.
Okay, thank you.
Yep. Now, I should mention that this idea of exploring von Hoff singularities as a way to generate unconventional superconductivity through repulsive interaction has been widely explored in several materials, going back to works on doped graphene, and more recently in graphene superlattices, in moiré materials, etc. But the problem in Hofstadter lattices had not been looked at. Okay, and that's the problem that I want to tell you about, which is the work that we had done. Okay, so the setting I want to consider is the following. I want to consider the Hofstadter-Hubbard model on a square lattice with repulsive on-site interactions. So I have electrons hopping on the sides of the square lattice. There's a magnetic flux phi threading each unit cell. I'll take this flux to be rational again, and this is my Hamiltonian. Okay, so I have here the non-interacting tight binding Hamiltonian, where the electrons are coupled to the external gauge field. So this would give me the Hofstadter bands, and what I'm doing is I'm adding a local on-site Hubbard interaction where U is repulsive. Okay, so here's something which I think it provides a perspective on why the systems are so special. So and it's the fact that because of the self-similarity of the Hofstadter bands, because they kind of repeat themselves as you tune the flux, as you change the flux, you also change the manifold of von Hoff singularities. So here's a very clear example of that. Suppose I start with 0 flux per unit cell, no magnetic field. This is my Fermi surface at half filling. Okay, so I have 2 von Hoff singularities, pi 0 and 0 pi. What I have is a single divergence. I have a single band who's with a log divergence at half filling. Now, suppose I go to pi flux. Pi flux means Q equals 2. That means I broke my magnetic Brillouin zone into 2 patches, which are related by translation vector by pi. And that means that I go from 2 von Hoff singularities to 4 von Hoff singularities. I have 1, 2, 3, and this one repeats here 4. Okay. So suppose I go to Q equals 3, which corresponds to 2 pi over 3 flux per unit cell. Now my magnetic below zone looks like this. There are 3 patches, and I go from 2 von Hoffs to 4 von Hoffs to 6 von Hoff singularities. So if I start with 2 von Hoff singularities at flux 1 over Q, I'm going to have 2 times Q von Hoff singularities. So here's a depiction of what these bands would look like. There's a reduction on the bandwidth. So if I start with a total bandwidth W, of course, each of these bands is going to have a reduced bandwidth, but they are not lambda levels. They still have a finite bandwidth, which is very important for what I'm going to do next. Why? Because next I'm going to say, what if I have a weakly, what if I have repulsive interactions? Okay, but let me consider these repulsive interactions to be weak. Okay, weak in the sense that they're going to be small than the characteristic bandwidth of each of these bands. Okay, since the bands start with a finite bandwidth, I can always take the interaction to be smaller than that. Lambda levels already have 0 bandwidth, so I can never access that regime. Okay, and that's something very different from these Hofstadter bands. Okay, so what I'm going to do is I'm going to build a model. Just do exactly like what you would do on the square lattice at 0 flux, but I'm going to do a model where I have 1 over Q flux per unit cell. What kind of model am I considering? I have a model in which there are 2 Q patches in this magnetic below zone. I know exactly the locations of the patches because those are the locations of the von Hoff singularities. They repeat themselves. These are not randomly distributed. It has to do with the self-similarity. And so I can write down with confidence what the effective theory is that between electrons, between electronic states on these von Hoff singularities. Looks like a sum of all the possible interactions that preserves momentum and charge conservation between these patches. There is an effective coupling constant over here, which at the bare level I can exactly calculate. Why? Because I know exactly where these von Hoffs are. So if I start from the Hubbard interaction, I project my interactions on a particular band, and then I further project on the von Hoff singularity. So I know exactly what the expression of this G is for each of these processes over here. And then I run my RG. Right now I say, let me consider all the possible processes that will occur over here, and let me start reducing my cutoff. Suppose I start with some cutoff here, away from this von Hoff singularity. Now let me start reduce it and flow towards the von Hoff singularity. How will my coupling constants change? It is at first it looks like a complicated problem, but it's a fun problem in organizing, or you just have a bunch of Feynman diagrams and you just need to do them. That's of course a beautiful picture of what you're doing, but of course in the end of the day you're writing equations that look like that. So the thing to appreciate over here is that the number of coupling constants changes as a function of the flux, because I have 2 Q patches, and Q is a parameter that can vary. However, as you look at these beta functions over here, which tell you all the possible fixed point trajectories of your RG, there's something very remarkable that happens. And what happens is that of all the possible fixed trajectories of the RG, you are always guaranteed that there is one fixed trajectory that reproduces the fixed point trajectory of the zero field problem. So in other words, if you take all this Q, if you take all these G couplings over here, M and N are patch indices over here. They are sort of scattering electrons between patches. If you make this G patch independent and you plug into the RG equation, you will find that it solves the RG equation. So in other words, there is, of all the possible fixed trajectories, there is one that is self-similar. In other words, that is one that really reproduces the behavior of the RG equations at zero field. That is very remarkable, because if you understand something about the flow of the RG at zero fields, and your microscopic interactions happen to realize that fixed point trajectory, you have a very universal understanding of what the physics is. This, I find this to be very remarkable, because look, you're looking at a very complicated band structure where a lot of stuff is happening, and you would think that the system somehow has lost memory of the zero field problem, but it hasn't. Okay. So here's some some numerical analysis of how these coupling constants flow, and they always start repulsive. And what really happens is that because of the renormalization coming from high energy modes, eventually the system develops a scale, and what you see over here is this coupling constant G1 over here becomes negative. So you start with a repulsive interaction, and the system generates an attractive channel, and this attractive channel is responsible for the onset of superconductivity in the systems. This is the Q equals 2 Ks at pi flux, and this is the Q equals 3 Ks at 2 pi over 3 flux. This fixed trajectory is not one of these self-similar fixed trajectories. It's some other one. So the system can realize many. It's a very rich phase diagram. However, at flux 1/3, we do find this to be the fixed point, which is very amazing, because we started with a very canonical interaction. I'm telling you that if you go to the square lattice at 1/6 filling with on-site repulsive Hubbard interactions, you will flow to that self-similar fixed trajectory. That is the statement, which we were very surprised to be true. Now, a little bit more details of the RG, and I should really think about wrapping up. Of course, we want to calculate the flow of the vertex and really track how superconductivity, spin density wave, and charge density wave susceptibilities grow or shrink as you flow into the RG. And this plots really tell you that within the assumptions of weak coupling RG that we are doing, superconductivity is the leading stability at a flux pi. The order parameter is very interesting. It changes sign across the patches of the Van Hoff singularities, very much like you would expect the D-wave superconducting cuprates to do. But it's a little bit more complicated order parameter in the sense that that you now have 2 sublattices per unit cell. But it's a D-wave-like order parameter in the sense that you're preserving time reversal symmetry. So if the order parameter changes sign between this point and that point of the Brillouin zone, it means it must cross through 0 somewhere. So we are guaranteed that this is a nodeless order parameter, and this is the D-wave-like version of superconductivity, except that we are at pi flux at 1/4 of the filling. Similar analysis happens for flux 2 pi over 3. Here we find that the order parameter becomes patch independent. That's the manifestation of the self-similarity I was talking about. We are breaking time reversal symmetry strongly. Nevertheless, we flow to a superconducting phase. Okay, that's extremely interesting. And we construct an order parameter that realizes that that phase, and we find that order parameter represents a chiral topological superconductor with chart number 6. Again, starting from repulsive interactions at the bare level, at low energies, the system develops an instability towards superconductivity. It's a very special type of superconductivity. It's topological, and the system would support 6 chiral Majorana edge states, which is a very interesting phase of matter. Now, this is kind of a summary of what we find. We find a competition of several of these instabilities. The problem is very rich because it really depends on which band you're feeling. There's really no universal answer to anything because there's a lot of information coming from the microscopics of the problem. The microscopics is showing In the flux, you have per unit cell. In the lattice, you have. In the bands you're projecting, in the filling you're looking at. So, there's a lot of possibilities of symmetry broken phases. But among these possibilities, we find superconductivity, which is extremely rewarding, given that Hofstadter systems are usually associated with quantum Hall physics. But of course, we also find spin density wave instabilities depending on which filling you're looking at. So I think it's a good time to end. Let me acknowledge it once again. My collaborators, Daniel Schaefer, who is a postdoc, is looking for a job. So if you're watching this video and you like the work, he's the person who really carried the heavy piano over here. And my former student John Wang, who is back in China. Our work, first part is published in PRB as an editor suggestion. It's a long paper, but we really try to understand several aspects of this problem that I think hadn't been really looked at very carefully. And thus the RG part is on the archive, and it's a paper under review. So this work is also supported by Dewey. Thanks for your attention, and I'm happy to take questions if you have.
Thank you, Luiz, for this very nice and didactic talk. So we are in the questions part now. Does anyone want to raise their hand or just open the microphone and ask a question? I have a couple of questions. So you are talking about triplet superconductivity, right? Because of the magnetic field.
This is singlet. That's right.
So
that's a great point.
Even with magnetic fields.
So it's singlet because I'm dealing with a Hubbard model. Okay. So that's a good point. So what is it we're doing? We in general breaking time reversal symmetry because of these fluxes, but we are working a regime where the spins are quasi-degenerate, right? So you can understand this in the limit where the Zeeman splitting is negligible in comparison with some pairing. So imagine, for example, that you understand the system at 0 Zeeman splitting, and you prove the onset of superconductivity. Now, if you turn on a small Zeeman coupling, superconductivity is not going to die immediately. So there's a regime at which this phase should survive. Of course, the triplet problem is something we are currently trying to understand, and that's a natural question. It's a natural extension of this work. Yeah.
Sure. The other question I have is that you are working with a single orbital all the time, right?
Single orbital in the sense of
you are in a lattice, so I assume you have an atom in each point of the lattice, and you are considering a single orbital in each one of these atoms. Okay. So do you think that this problem could be solved using random phase approximation, like it was done for the pnictides, for the cuprates, right at the beginning when people didn't know that it was very strong correlations?
Right. There's of course some influential work by Scalapino et al. And a bunch of other people, right? Providing a picture for why D wave makes sense on the and it has to do with the proximity to a spin density wave order, right? That fluctuates, so the subtlety shows an enhancement at pi wave vector.
Exactly.
You can make that qualitative argument, but I think we are going beyond here because we are really not assuming anything, right? We are doing an RG. Of course, we are assuming we're coupling. That's the only assumption we are making, and we are really letting all these channels talk to each other. SDW, superconductivity, CDW, and making no assumptions other than that. So we are just really bringing out the cutoff, reducing the cutoff, and really seeing how these phases are talking to each other. But I think your question is very good. I think qualitatively, it's the proximity to a spin density wave instability that is fostering superconductivity. And in fact, we see this. We see that when we track the the superconducting susceptibility and SDW susceptibility, initially SDW grows because we have repulsive interactions with nesting, so it grows, and the growing of SW instability tends to bring the superconducting instability up, but eventually they cross, and eventually superconductivity dominates and really shows up as the leading stability. So there's some truth to that, but I don't think the RPA really captures the whole story.
Sure.
But it captures part of the story. Yeah.
Sure. And there is a question from Rodrigo Pereira, if you can read it or in the chat.
Oh, hi, Rodrigo. Yeah. Oh, right. Is there a version? Yeah. Okay. You wanna? Should I read the question or?
I can read it. Hi, Luiz, great talk. Is there a quasi 1D version of these phases that one could look for in ladders or narrow cylinders?
Yeah, great question. Presumably, yes. Presumably, that's actually a fantastic question. Presumably, by looking at, we haven't gone to that analysis because we really, really exploring more like the 2D aspect of the system, and then looking at the von Hoff singularities. But I can imagine a regime where you start from ladders, right? And try to think about the system as a quasi 1D system, and then perhaps do some bosonization and then you could imagine a couple wire construction of the systems, for example, right? If you understand how these ladders behave. I think yes. I'm not sure if I have anything more insightful to say other than it's a great question, and one can definitely look into that. Yeah.
Okay, we have a question from Rafael. Rafael, please.
Yeah, thank you, Professor Luiz, for the very nice talk. Can you please go to the summary where you put some nice graphics? DM.
My slide's a bit slow. Oh.
Yeah, right there. So for nodal superconductivity, do you have? Is it that I see a pseudo gap in there?
A pseudo gap. Well, I would be a little hesitant to call it a pseudo gap. I think to see a pseudo gap, you really have to be in some kind of strongly correlated regime, and that's not what we are doing. We are really at weak coupling. So I think what you really have is you have an instability from a fermiliquid, from a normal fermiliquid into a D-wave superconductor. Yes.
Right. But could you explore, I don't know, some duality in your model to infer something about the strong coupling regime?
Good question. Some duality. I am not sure. What do you have in mind by duality exactly?
Yeah, in the sense of weak strong coupling. In the sense.
Yeah, well, potentially. I mean, dualities are not easy things to find, right, to identify, but I don't know how to tackle this problem in general. If there would be some duality, lurking in the background would be great. But I so far haven't thought about how to identify one. Yeah.
Yeah, and last question: have you read something like, I don't know, DMRG or something to investigate the strong coupling limit?
Yeah, I have. I know. I have a student who is starting to do that. Yeah, great question. We'll keep you posted. But if you have interest, we can also talk.
Perfect. Thank you.
Edson, any questions?
Yeah. Hey, hi. Thank you, Luiz, for a very nice talk. A little bit hard to follow for those who are not familiar with, like myself. So, but my question, I have a few questions, but I think some of them was already tackled by the previous question. So, first, first, I would like to comment on Rafael's last question about the MRD calculation. I think that would go along, or at least close, or it's connected to Rodrigo's question, because if you find the likewise one-dimensional model, then it would be easy to apply the MRD, because this is more useful for was 1D mature system, right? So in the true 2D, still questionable, I guess, how the MRD would work. So this it's something that came to my mind. So my question here is now is regarding your one whole singularity. When you have your one whole singularity here, you are working on a 2D lattice with this particle symmetry. So even though if you apply the magnetic flux, I think particle symmetry is still preserved. Have you thought about what kind of, or if this instability or this Cooper pair instability would still be the dominant if you are in a particle asymmetric one whole singularity, so to speak?
Yeah, I don't think it depends on that. I think that's just a special feature of the square lattice. For instance, graphene. In graphene, like zero field graphene, right? You have a one-half singularity, which is away from a half filling, right? And there, you can predict, a chiral D wave superconductivity through NRG analysis. That itself is, I don't think it's an important aspect of.
So you don't need that.
So one can extend this to hexagonal lattices, for example. Yeah. And
but fact, hexagonal lattices still have particle. Oh yeah, this whole singularity away from particle symmetric point. Yeah, right.
Yeah. I mean, in graphene, they would have three of them on the points M1, M2, and M3, which are between the values of the between K and K prime.
So
right?
you actually don't need these arguments, right, to get your result.
No, not at all. Yeah.
Okay, more general than that.
Yeah.
So would you expect some different type of superconductivity other than D wave in like a more complex singularity, for instance?
Yeah, I think the details of the band structure matter a lot. So what happens is that, let me maybe give you right. So what happens is the following. So you have a set of RG equations, right? You have a set of beta functions, and then in principle you can try to classify all the possible fixed point trajectories of this RG. Now, to which one you flow depends on the bare couplings, right? Your starting point, and the bare couplings depend on what? Depend on the sort of the nature of the bare interaction you put in. They depend also on the projection of these interactions onto the bands and onto the Van Hoff. So the use here are spinors, single particle spinors that take you, let's say, from the sublattice representation to the band representation, right? And they also depend on the position of this Van Hoff singularities K. So, it's like these spinors are winding in K space, right? So you're computing something that could depend on a spinor that's pointing here on this Van Hoff singularity, but maybe it's pointing there, or maybe it's pointing like this. So there's a texture, there's a structure of the single particle states that reflects the flux you are, that reflects the lattice you are, that reflects the band you're projecting, and everything that's really showing up in the bare interactions, right? So presumably by changing the bare interactions, you can flow to a different fixed point trajectory and realize some other phase. So yeah, I mean, all this is very important, and it's like telling you something important. Tell the microscopic physics matter, right? To selecting which of these winning stabilities you realize. So it's very rich. If you change the lattice, change the structure of von Hofs, etc., you might get new fixed points.
Very good. What the last question? What the Majorana modes or chiral Majorana modes, are they still time reversal symmetric Majorana mode?
No, they're broken. Yeah, time. So it's a chiral phase with char number 6. Yeah, we're in a broken time reversal symmetry phase here. It's a flux 2 pi over 3, and there will be 6 of them each.
So they're broken because of the flux only, right?
Yes, yes.
But they still have Zeeman. Zeeman is 0.
No Zeeman here, but the band structure,
it
breaks time reversal. That's right.
So this is essential.
It's degenerate, but broken time reversal.
So this is essential for the Majorana mode.
Yes, as far as we know, yeah. I mean, of course, you could realize a superconducting phase with 0 char number, right? It would be just a different kind of superconductor, but well, this one happens to be a char number 6.
Okay, thank you very much. Very good talk, by the way.
So, last question. Do you need the Fermi energy to be at the Van Hove singularity to see superconductivity?
Well, near the Van Hove singularity, right?
Near,
so what's happening,
okay.
as you tune, I mean, if you're really crossing the Van Hove singularity, then you are in this regime of perfect nesting, you're gonna have a log divergence, right? That dominates. As you move away, then this log starts to have a
but there would be the sweet spot, right, for a very strong superconductivity. So as you increase Q, I saw that you increase the number of Van Hove singularities. You could gate the system and move the Fermi energy from Van Hove singularity to Van Hove singularity. Do you see qualitatively the same superconducting order? Did you check on that, or?
Oh no, great question. No, in fact, no. So this is, for example, the summary, right? So let's look at QCOS. Let's look at QCOS 3. So in QCOS 2 pi flux, we only see D wave-like superconductivity, either at 1/4 or 3/4. So there are two spots. At flux 1/3, there are 3 bands that are separated by a gap. So on the lowest and highest bands, we see this chiral topological superconductivity that dominates once you slightly break away from nesting. And in the middle band, this is a typo. This should be SDW. My apologies. Instead of CDW, it should be SDW. This is an SW instability over here, right? Okay. So as you tune your Fermi level, and that's precisely what I was saying before. It really depends on which band you're targeting. There can be a difference, right, in the kinds of instabilities that you see. So that is an example precisely of that. Okay, great. Very, very nice talk, very didactic, and for us who did some superconductivity in the past, it's very interesting to see that it's still alive despite all the topological insulators that have taken charge of the frontier physics. So it's nice to see that there is still a lot of superconductivity to be done.
May I have a last question?
Sure.
This goes into along Rafael's question, but you may not. You may be away from that regime. So, would you expect some interesting interplay between superconductivity, instability, and Mott regime in the strong coupling, the strong interactivity?
Well, that's a good question. That's sort of like exploring another side of the phase diagram, right? Yeah. Where
maybe hard to it may have to
It's
say,
possible.
because
It's possible that that there's a strong coupling argument for why spin fluctuations could in the setting of, let's say, of the TJ model, right? As you move away from half filling and you let holes propagate to the lattice, one can try to understand what if the presence of fluxes on the lattice can lead to some interesting superconductivity. That has usually done as a mean field argument, right? So so requires you some it requires some faith that something is going to happen, and then you put in by hand and sort of try to see what happens. So it's not a as an unbiased calculation as the one that I described. Of course, I'm at weak coupling, so I can do more progress at weak coupling. But yeah, it's a great question. It could very well be there's some rich interplay between spin fluctuations and these phases as you move away from a Mott transition.
Good, thank you.
Okay, so if we don't have any more questions, we should thank the speaker again. Thank you very much for this very nice talk. I'm going to be sending you an email asking for the slides so that we can post together with if you don't mind, that we post together with the video.
Okay,